Dear students, welcome back to my YouTube channel LS-05 and this is an online chemistry tutorial, and you get my previous videos after visiting my personal homepage or from my YouTube channel. And we were discussing the topic chemistry of functional group 1, and we already discussed the halogen compounds and alcohol. And today I'm going to discuss with you the phenol and its preparation and comparison of acidity of phenol and preparation and the uses of phenol. So these are our learning objectives, and prepare phenol from chlorobenzene and compare the acidity of phenol, orthonitrophenol and p-methoxyphenol, and as I said, preparation and uses of phenolphthalein. Phenol, we already know that it's an aromatic compound having hydroxy group OH directly attached to the benzene ring. And this is the structure of phenol. And in phenol, the hydroxy group is attached to an sp2 hybridized carbon atom, and that is benzene. All carbon atoms are sp2 hybridized, and hydroxy group attached to one of the sp2 hybridized carbon atom of aromatic ring, and the oxygen atom of hydroxyl group has two lone pairs of electron, and the bond angle is 109 degree. Next one, classification of phenol. There are three types. Depends on the number of hydroxyl group. You can classify phenol into 3 monohydric, example is phenol, and 2-methylphenol, that is also called orthocresol. And next one, dihydric phenol, contains 2 hydroxy group, and for example, it is also called 1,2-dihydroxybenzene or catechol. And 1,3-dihydroxybenzene is another example of dihydric phenol, which is also called resorcinol. Third category is trihydric phenol, and 1,2,3-trihydroxybenzene, it is called pyrogalol. And the next one is 1,2,4-trihydroxybenzene, it is called hydroxyquinol. Okay, next one is nomenclature, and the simplest member of series is phenol. And next one you can say as a derivative, and usually the derivative named as a derivative of parent compound. This is parent compound phenol, and the derivative, that is chloroderivative, you have to name it as 2-chlorophenol, derivative of phenol. And next one is this is para-nitrophenol, also it is called 4-nitrophenol. And the next one is 4-chloro, this is 4-chloro-2-nitrophenol. There are some trivial names like when a phenol contains SCH3 or SCH3 group at ortho or meta or para position is called cresol. If CH3 is at ortho, it is called orthocresol, and it is in metacresol, and if it is in paracresol. Similarly, there is a catechol, and this is ortho-dihydroxybenzene, and this is a meta-dihydroxybenzene resorcinol, and this para-dihydroxybenzene hydroquinol, and the trihydroxy pyrogalol, and this is 135 trihydroxybenzene, that is fluoroglucinol. Next one is preparation of phenol from chlorobenzene. Usually, aryl halides on hydrolysis yield phenol, and this process is not simple because halogen attached to a benzene ring does not undergo a central reaction. Do you know why? Because this CX bond is resonance stabilized. So this chlorine can, the lone pair on chlorine can undergo a delocalization with the benzene ring. So this bond is little bit stronger than as we expected. So it is difficult to break this bond, Cl bond, because of its resonance stabilization. Hence, the reaction takes place at high pressure and elevated temperature is required to break the C-Cl bond. And the process is like this, treating chlorobenzene with sodium hydroxide at very high temperature, that is 350 degrees Celsius, and very high pressure, 320 atmospheric pressure. And you get first sodium phenoxide, and this is on acidic hydrolysis, you get phenol. And this process is a very well-known process. It is known as DOS process, the name of a chemical company. And another strategy to make a phenol is if you have some electron withdrawing group attached to the benzene ring, the condition of reaction may become simpler. You can see it here. If you have one electron withdrawing group here and you need less temperature here, and if you have a two electron withdrawing group here at this nucleus and you need a very mild condition and mild base and little bit lower temperature, and the process becomes simpler. And this is the next strategy to make phenol. And here you have three electron withdrawing group and you need very little temperature and a very mild base condition. Okay, that's all about preparation. Next one is comparison of acidity of phenol, para-nitrophenol and para-methoxyphenol. And reaction of phenol with metals like sodium or aluminum or with base sodium hydroxide, and it gives alkoxide, corresponding alkoxide. This indicates the phenol is this hydroxyl or H is an acidic in nature, and this can donate H plus ion and in acid base reaction. And this alcohol, in presence of base, it can grab this proton and it form corresponding alkoxide. And this acid lose H plus and it form alkoxide. And this alkoxide is known as the conjugate base of this acid. So conjugate base means that is the compound which is obtained after the removal of H plus, that is conjugate base, and this is conjugate acid. So in the case of alcohol, on ionization, you get this conjugate base alkoxide and H plus, and this is in aliphatic alcohol, and this is in phenol. This is the conjugate base of phenol, that is phenoxide ion. It's a conjugate base of phenol, and the extent of ionization depends on the stability of this conjugate base. Okay, so in the case of phenol, the extent of ionization, that is the equilibrium will be shifted more towards right direction if this phenoxide or conjugate base is highly stabilized. Next one, the stability of phenol and phenoxide. Here, which one is more stable one? The stability can be explained based on charge delocalization, and in both cases, and these are some resonance stabilized. These both compounds are resonance stabilized, and in the case of phenol, this is the resonance structures, various resonance structures of phenol. And the lone pair on here can undergo in resonance with this aromatic ring as shown here. And first you can show it like this. This lone pair is transferring electron towards here, then it becomes double bonded, and this double bond break, and you have to show this negative charge here. And then again, and you can show the arrow like this, and this double bond break, and this carbon becomes anionic. Similarly, it transfers, show the like this, transferring electron like this, and you get a negative charge here. And in all these four structures, you get this as the resonance hybrid resonance structure of phenol. And you can see here in phenol there is a negative charge and positive charge here. So there is a charge separation. Whereas in the case of phenoxide, you can see that there is no charge separation in resonance structure, and this negative charge is delocalized all over the system. So here the charge is not completely delocalized like phenoxide. So this we can say this is comparatively stabilized system, but it is very strongly stabilized. So phenoxide is very strongly stabilized system. Why it is very strongly stabilized? Because it is 100% charge delocalization occurs in the case of phenoxide ion. But in phenol, you can see that there is a charge separation, and then energy will be a little bit disturbed, and it will be having higher energy, and this will be having a lower energy, and highly charged stabilization occurs in phenoxide ion. So here there is a possibility of shifting equilibrium towards this direction if you put some bases into the system, and we can say this is a acidic compound because it forms highly stabilized conjugate base phenoxide ion. And next we are looking at what happens to this phenoxide ion stability when you attach some groups like electron withdrawing group like NO2 or aldehyde CHO or carboxylic acid or cyano. Such electron withdrawing group attached to this nucleus. What happens to the stability of conjugate base? So it can stabilize this anion or negative charge, because here you can see that this negative charge, it can attract this negative charge, this electron withdrawing group. It is electron withdrawing, so it can attract the negative charge, and this negative charge will be delocalized or not localized on this oxygen atom. It is delocalized all over the molecule. Then the system will be highly stabilized. So any factor that is that can delocalize a charge over the whole system can stabilize the molecule. And at the same time, when you use electron withdrawing group like alkyl group or NH2 group or alkoxy group, it has an entirely opposite effect. It destabilizes the phenoxide. Why? Because it is donating electron or releasing electron density towards this oxygen anion. So it increases electron density on oxygen anion. So it is localizing charge on some atom. So there is no delocalization. So when you attach some electron donating group here, the acid strength become decreases. So nitrophenol, so you can compare the acidity of phenol, para-nitrophenol and para-methoxyphenol. In the case of para-nitrophenol, so if you have an electron withdrawing group, it can increase the acidity, and when you have an electron donating group, it can decrease acidity than phenol. And this can be more evident from the resonance structure. When you have an electron withdrawing group para-nitrophenol, it stabilizes the phenoxide ion by dispersing the negative charge relative to phenol. And this is the resonance structure of para-nitrophenoxide anion, and you can see that the communication or charge transfer take place not only to the ring and also to the this NO2, and you can see that there is a communication between these two, this benzene and functional group. So you can see that the negative charge on oxygen is delocalizing all over the molecule here. So it is completely delocalizing. But when you have an electron donating group or para-methoxyphenol, it destabilizes the phenoxide by donating electron density. You can see that these electron densities are donated towards this direction, and this carbon becomes negatively charged, and there is a lot of charge is accumulated on this oxygen atom, and it destabilizes. Actually, charge is localized over one atom instead of delocalized over all over the molecule, so it can destabilize. So this is less acidic. Next one, phenolphthalein preparation and its uses. Phenolphthalein, this is the structure of phenolphthalein, and phenolphthalein is prepared by heating phthalic anhydride. This is called phthalic anhydride. And phenol, with phenol and 2 equivalent of phenol, 1 equivalent of phthalic anhydride, in the presence of dehydrating agent like zinc chloride, and it undergo a dehydration, water elimination take place, and it form a structure like this, phenolphthalein. And phenolphthalein, we already have been used this one as an acid-base titration as an indicator, and which is also used in toys as a component of disappearing ink, and it is also used in medical uses as a laxative. Okay, that's all about the phenolphthalein. In summary, we have learned how the phenol can be prepared from chlorobenzene by Taus process, and what is the effect of electron withdrawing and electron donating group at para-position of phenol on acidic properties of phenol. And we found that para-nitrophenol is more acidic than para-methoxyphenol. And we also learned preparation of phenolphthalein and its uses. Okay, that's all. Thank you for watching.